The moment your water stops being safe, the clock starts ticking in a way most people fundamentally misunderstand. Dehydration is not the first threat. Infection is. Long before your body shuts down from lack of fluid, microscopic organisms begin to colonize your system, exploiting every vulnerability with ruthless efficiency. In a collapse scenario, whether triggered by infrastructure failure, contamination events, or supply chain breakdown, the assumption that clear water is safe water becomes a fatal mistake, because the most dangerous water you will ever drink is the kind that looks perfectly clean. This is where the real danger begins, not with visible pollution, but with biological invisibility. Pathogens such as bacteria, viruses, and protozoa operate on a scale that bypasses human intuition. You cannot smell them, you cannot see them, and in many cases you cannot taste them. Yet their impact is immediate and compounding. A single exposure to contaminated water can introduce organisms like E. coli, Giardia, or Cryptosporidium into your digestive system. These are not minor inconveniences. They trigger severe gastrointestinal distress, leading to rapid fluid loss, electrolyte imbalance, and ultimately a cascade toward organ failure if untreated. In a stable environment, modern medicine compensates for this. In a collapse, there is no safety net. The analysis becomes more severe when you consider how most people attempt to solve this problem. The default assumption is boiling. Heat the water, kill the pathogens, and move on. This is partially correct, but dangerously incomplete. Boiling is effective against biological contaminants, but it does nothing to remove chemical toxins, heavy metals, or particulate matter. In fact, boiling can concentrate certain contaminants by reducing water volume through evaporation. If your source is compromised by industrial runoff, agricultural chemicals, or even naturally occurring arsenic, boiling transforms your safe water into a more concentrated hazard. The misunderstanding here is rooted in oversimplification. People treat water purification as a single-step solution when it is, in reality, a layered process requiring multiple barriers. This is where the hidden science begins to reveal itself, and where most survival advice fails to go deep enough. Water purification is not about a single method. It is about redundancy through filtration, adsorption, and disinfection. Each stage targets a different category of threat. Filtration removes particulates and larger organisms. Adsorption, typically through activated carbon, binds chemical contaminants. Disinfection neutralizes biological agents. The forbidden aspect of this method is not that it is secret, but that it is consistently overlooked because it requires more effort, more understanding, and more precision than most people are willing to apply under stress. Consider the structure of a multibarrier system. At its core, it mimics municipal water treatment on a smaller scale. The first stage is mechanical filtration. This can be achieved through layered materials such as sand, gravel, and cloth, or through portable filters rated in microns. The purpose is to physically remove suspended solids and reduce turbidity. Turbidity is not just an aesthetic issue. Cloudy water shields microorganisms from disinfection processes, allowing them to survive treatments that would otherwise be lethal. By reducing turbidity, you are not just improving clarity, you are increasing the effectiveness of every subsequent step. The next stage introduces adsorption, a concept often misunderstood. Activated carbon does not filter in the traditional sense. It attracts and holds chemical compounds on its surface through intermolecular forces. This includes chlorine, pesticides, volatile organic compounds, and certain heavy metals. The effectiveness of this process depends on surface area. Activated carbon is engineered to have an immense internal surface, often exceeding 1,000 square meters per gram. This is why a small amount can have a disproportionate impact. However, it is not infinite. Once the adsorption sites are filled, the carbon becomes ineffective, a limitation rarely acknowledged in simplified survival advice. The final stage is disinfection, where biological threats are neutralized. This can be achieved through boiling, chemical treatment, or ultraviolet radiation. Each method has its strengths and limitations. Boiling is reliable but resource-intensive. Chemical disinfectants like chlorine or iodine are lightweight and effective, but require precise dosing and contact time. Ultraviolet light is highly efficient, but dependent on clear water and a functioning device. The hidden principle here is synergy. No single method is sufficient under all conditions, but when combined, they create a system resilient enough to handle a wide range of threats. Evidence for this approach is not theoretical. It is embedded in decades of public health data and emergency response protocols. Municipal systems worldwide rely on multibarrier treatment because no single method can guarantee safety. In disaster zones, organizations implement layered purification strategies to prevent outbreaks of waterborne disease. The reason is simple: redundancy saves lives. When one barrier fails, another compensates. In a collapse scenario, adopting this same logic on an individual level is not optional. It is the difference between sustained survival and rapid decline. The survival implications extend beyond immediate health. Water quality directly impacts decision-making, mobility, and resource allocation. If your water source is unreliable, you are forced to spend more time and energy securing alternatives. This increases exposure to environmental hazards, reduces your ability to rest, and accelerates fatigue. Contaminated water does not just make you sick, it destabilizes your entire survival strategy. Every hour spent recovering from illness is an hour not spent securing food, shelter, or security. As the situation escalates, the margin for error narrows. Early in a collapse, you may have access to relatively clean sources, stored water, bottled supplies, or functioning infrastructure. Over time, these degrade or disappear. What remains are surface water sources increasingly exposed to contamination. Rainwater, often considered safe, can carry airborne pollutants. Rivers and lakes become collection points for upstream contamination. Groundwater, while generally safer, can be compromised by geological or industrial factors. The assumption that any source is inherently safe becomes progressively less valid. This is where the transition occurs from reactive to proactive survival. Waiting until you are desperate to purify water is a losing strategy. The systems and knowledge must be in place before they are needed. This includes understanding your local environment, identifying potential water sources, and preparing the materials required for multi-stage purification. It also means recognizing the limitations of each method and planning accordingly. Improvisation has its place, but it is not a substitute for preparation grounded in scientific understanding. And as the pressure builds, as resources dwindle and conditions deteriorate, the question is no longer whether you can find water, but whether you can make it safe consistently under any condition, with limited tools and no margin for failure. Because in a true collapse, the threat is not scarcity alone. It is the silent, invisible contamination that turns survival into a race against time, a race most people lose not because they lack water, but because they misunderstand it. The failure point most people never anticipate is not the absence of a purification method, but the gradual breakdown of that method under repeated use, environmental stress, and human error. In the early phase, when tools are new and conditions are controlled, even basic filtration or chemical treatment appears reliable. But survival is not measured in hours or days. It is measured in sustained exposure, repetition, and the compounding effect of small mistakes. A filter that clogs, a chemical dose that is slightly off, a container that is not fully clean, these are not isolated errors. They accumulate, and over time, they create a system failure that is difficult to detect until symptoms begin to appear. To understand this, you have to analyze water purification not as a single action, but as a process chain with multiple points of vulnerability. Each stage, collection, storage, filtration, adsorption, and disinfection, introduces its own risks. The common misunderstanding is to treat purification as something that happens only at the moment of treatment. In reality, contamination can occur before and after that moment. Water collected from a relatively clean source can become unsafe through improper handling. A purified batch can be recontaminated through storage in unclean containers or exposure to hands, tools, or surfaces carrying pathogens. The hidden science here is not just about removing contaminants, but about maintaining a controlled pathway from source to consumption. One of the most overlooked principles is contact time. Whether you are using heat, chemicals, or ultraviolet light, effectiveness is not instantaneous. It depends on sustained exposure under specific conditions. Boiling water for a few seconds may not be sufficient at higher altitudes, where the boiling point is lower and heat transfer is less effective against certain organisms. Chemical disinfectants require precise timing to penetrate cell walls and disrupt metabolic processes. Ultraviolet systems depend on consistent exposure across all water particles, which becomes impossible if turbidity is too high. The misunderstanding is assuming that the method itself guarantees safety, when in fact, it is the correct application of that method over time that determines the outcome. The deeper layer of this problem involves scale and load. In a controlled environment, purification systems are designed for predictable volumes and contamination levels. In a collapse scenario, both variables become unstable. You may be forced to process larger quantities of water with limited equipment or deal with sources that are heavily contaminated beyond the capacity of your system. This creates a mismatch between demand and capability. The result is either undertreatment, where contaminants remain, or overuse of resources, where filters degrade rapidly and chemicals are depleted faster than expected. The hidden insight is that every purification system has a threshold, and exceeding that threshold does not result in partial effectiveness. It results in failure. Evidence of this can be seen in field reports from disaster zones, where initial access to purification tools does not prevent outbreaks of waterborne illness. The issue is rarely the absence of technology. It is the inability to maintain proper usage under stress. Filters are used beyond their lifespan, chemical treatments are applied inconsistently, and storage protocols break down. These are not theoretical risks. They are documented patterns that repeat across different environments and crises. The lesson is clear. Reliability is not built into the tool. It is built into the system of use. This leads to a critical survival implication. Redundancy must extend beyond methods to include behavior and process control. It is not enough to have multiple ways to purify water. You must also have consistent procedures for how water is handled at every stage. This includes separating raw and treated water containers, minimizing direct contact, and ensuring that every step is repeatable under fatigue and stress. The more complex your system, the greater the risk of error. The goal is not maximum sophistication, but optimal reliability. As conditions worsen, another layer of risk emerges: biofilm formation. This is a process where microorganisms adhere to surfaces and create protective matrices that allow them to survive and multiply. Containers, filters, and even tubing can become breeding grounds if not properly maintained. Biofilms are resistant to many forms of disinfection, making them particularly dangerous in long-term scenarios. The water passing through a contaminated system may appear clear and taste normal, yet carry a persistent microbial load. The misunderstanding here is assuming that cleaning is a one-time action, rather than an ongoing requirement tied to usage frequency and environmental conditions. The science behind biofilms reveals why they are so resilient. The extracellular matrix they produce acts as a barrier, reducing the penetration of disinfectants and shielding the organisms within. This means that standard treatment methods may not fully eliminate them once established. Prevention becomes far more effective than removal. Regular cleaning, drying, and when possible, exposure to sunlight or heat can disrupt early formation. But once a mature biofilm develops, the system itself may need to be replaced or thoroughly decontaminated, a process that is often impractical in a resource-limited environment. This is where the concept of system degradation becomes unavoidable. Every component you rely on, filters, containers, seals, and even the water sources themselves, changes over time. Materials wear down, effectiveness decreases, and risks increase. The longer the timeline, the more your survival depends on anticipating these changes rather than reacting to them. This requires a shift in mindset from short-term problem solving to long-term system management. You are not just purifying water. You are maintaining a dynamic system under continuous stress. The escalation continues as environmental factors begin to interfere more aggressively. Temperature fluctuations affect chemical reaction rates and microbial growth. Warmer conditions accelerate bacterial reproduction, increasing the contamination load you must handle. Colder conditions can reduce the effectiveness of chemical treatments and make physical processes more difficult. Seasonal changes alter water availability and quality, introducing new variables that must be accounted for. The assumption that a single method will work consistently across all conditions becomes increasingly unreliable. At this stage, the margin for improvisation narrows even further. The ability to adapt your purification approach based on changing conditions becomes critical. This might involve adjusting contact times, increasing filtration stages, or prioritizing certain water sources over others. The hidden principle is flexibility grounded in understanding. Without a clear grasp of why each method works, adaptation becomes guesswork, and guesswork in this context leads to exposure. And as the system strains under pressure, a final layer of risk emerges: human perception. Fatigue, stress, and urgency distort judgment. The longer you operate under survival conditions, the more likely you are to cut corners, skip steps, or trust assumptions that would not hold under normal circumstances. This is not a failure of discipline. It is a predictable response to sustained stress. The only way to counter it is through systems that are simple enough to execute reliably, even when your cognitive capacity is reduced. The transition at this point is unavoidable. What began as a technical challenge, making water safe, has evolved into a complex interaction between environment, equipment, and human behavior. The threat is no longer just contamination. It is the gradual erosion of the systems designed to prevent it, and as those systems weaken, the risk does not increase linearly. It accelerates, pushing you closer to a threshold where recovery becomes difficult, and every decision carries amplified consequences. At the final stage, the problem of water is no longer technical in isolation. It becomes systemic, embedded in every aspect of survival, and governed by one overriding reality: you are not trying to achieve perfect purity, you are trying to manage risk under constraints that are constantly tightening. The idea of safe water begins to shift from an absolute condition to a probabilistic one. Every sip carries a level of uncertainty, and your objective is to reduce that uncertainty as much as possible, as consistently as possible, over time. This is the point where most survival strategies collapse, not because the methods stop working entirely, but because the user fails to adapt to the changing balance between effort, resources, and risk. The danger now escalates through accumulation rather than immediate failure. Low-level contamination that might not cause acute illness in a single exposure begins to compound across days and weeks. Subclinical infections, minor gastrointestinal disturbances, and gradual dehydration interact in ways that weaken the body without triggering obvious alarms. This is the hidden pathway to collapse, not a dramatic event, but a slow degradation of physiological resilience. Your immune system, already strained by stress, reduced nutrition, and environmental exposure, becomes less capable of handling even minor pathogen loads. What was once survivable becomes critical. The analysis at this stage reveals a crucial misunderstanding that persists even among those who have prepared: the belief that purification is a discrete task with a clear endpoint. In reality, it is a continuous cycle that must be integrated into daily survival behavior. Water is collected, treated, stored, used, and then the cycle repeats, each iteration introducing new variables and potential points of failure. The hidden science here is feedback. Every outcome, good or bad, provides data about the effectiveness of your system. Changes in taste, clarity, odor, or physical response are signals that must be interpreted, not ignored. The absence of immediate illness does not confirm safety. It only indicates that the threshold of harm has not yet been crossed. Evidence from prolonged field operations and historical survival scenarios shows that those who endure are not necessarily the ones with the most advanced tools, but the ones who maintain consistent, disciplined processes. They monitor their systems, adjust based on observed outcomes, and avoid complacency. This is not instinctive behavior. It is learned through understanding and reinforced through repetition. In contrast, failure often follows a predictable pattern: initial diligence, followed by gradual relaxation of standards as fatigue sets in, leading to a critical lapse that introduces contamination at a scale the body cannot handle. The survival implications become stark. At this point, your capacity to secure food, maintain shelter, and defend yourself is directly tied to your physical condition, which is in turn dependent on water quality. A compromised water system does not just threaten your health, it undermines every other survival function. Weakness reduces mobility, slows reaction time, and impairs decision-making. Even mild dehydration can significantly affect cognitive performance, increasing the likelihood of errors in already high-risk situations. The system is interconnected, and water sits at its core. As pressure continues to build, the concept of prioritization becomes unavoidable. You may not have the resources to treat all water to the highest possible standard. Decisions must be made about when to invest time and energy into full multi-stage purification and when to accept a higher level of risk in exchange for conserving resources. This is where the forbidden aspect of the method fully emerges, not as a secret technique, but as an uncomfortable truth. Absolute safety is not always achievable. Survival depends on informed compromise. Understanding which risks are acceptable and which are not requires a deep grasp of contamination types, exposure levels, and your own physical condition. The hidden principle guiding these decisions is risk layering. Not all contaminants carry the same immediate threat. Biological pathogens often present the highest short-term risk, capable of incapacitating you within days. Chemical contaminants, depending on type and concentration, may pose longer-term risks that are less immediately debilitating. This does not make them safe, but it changes how you prioritize treatment under constraint. In a situation where resources are limited, ensuring effective disinfection may take precedence over complete chemical removal, especially if the exposure window is expected to be short. These are not ideal choices. They are calculated trade-offs grounded in survival logic. The escalation reaches its peak when external conditions remove even the possibility of optimal treatment. Equipment fails, supplies run out, and environmental conditions degrade to the point where every available water source is compromised. At this threshold, the focus shifts from optimization to mitigation. You reduce exposure where possible, increase intake frequency to avoid severe dehydration, and rely on your body's remaining resilience to bridge the gap. This is the edge of survivability, where preparation, knowledge, and adaptability are tested simultaneously. And yet even here, the underlying science continues to apply. Pathogen load still matters, contact time still matters, handling still matters. Small improvements in process can produce disproportionately large reductions in risk. A slightly longer boil, a cleaner container, a more careful separation between raw and treated water, these are marginal gains that accumulate in your favor. The system may be degraded, but it is not irrelevant. Every action still influences the outcome. The final transition is not about technique, but about mindset. Water purification is no longer a task you perform. It becomes a discipline you live. Every interaction with water is deliberate, informed, and controlled to the extent possible. There is no assumption of safety, only continuous verification. There is no reliance on a single method, only the integration of multiple barriers adapted to current conditions. And there is no room for complacency, because the consequences of error are immediate and unforgiving. In the end, the forbidden method is not hidden because it is unknown. It is hidden because it demands more than most are willing to give under pressure: sustained attention, disciplined execution, and a willingness to confront uncomfortable trade-offs. It replaces simplicity with complexity, certainty with probability, and convenience with control. But in a true collapse, these are not disadvantages. They are the conditions of survival. Because the reality is this: water will always be available in some form. The question is whether you can transform it consistently and reliably into something your body can use without turning against you. And that is not a question of luck or access. It is a question of understanding, applied without interruption, for as long as the system around you remains broken.